Modern traffic networks are chaotic, high-dimensional environments. When heavy rain hits a multi-level interchange, while connected vehicles broadcast conflicting anomaly reports, and dense multimodal congestion chokes the off-ramps, human operators cannot process the resulting flood of variables in real time. To manage this, departments of transportation typically rely on what is called a scalar reactive intelligent transportation system. This architecture evaluates traffic through isolated single-variable data points, like local queue length at one intersection or the occupancy of a single lane. Because sensing and signaling are decoupled across a fragmented array of dashboards, the system acts only after the breakdown occurs. A queue must grow before the controller compensates. An anomaly or incident is only logged after the damage has cascaded through the corridor. Adding isolated artificial intelligence detectors to these legacy screens does not solve the underlying lag. The core architecture itself lacks the capacity for system-wide predictive governance. A formal solution exists in a white paper outlining the Predictive Tensor Control Plane, or PTCP, and Tensor-Network Quantum Gravity, or TNQG. This framework moves away from disconnected scalar rules. It aggregates all variables into a unified state tensor, treating the entire transportation network as a single operational geometry, where every lane, signal, and connected device exists as a coordinate in a shared mathematical space. The document presents a formal non-equivalence proof. It identifies 5 structural primitives required to achieve safe system-wide traffic automation. As the conclusion block at the bottom of the stack shows, this is a mathematical requirement. If an intelligent transportation architecture lacks any of these 5 primitives, it is formally unequipped for next-generation automation. To construct a predictive control plane capable of handling modern congestion, we must implement each of the 5 primitives on this stack. Primitive 1 requires high-dimensional state tracking. A true network controller must evaluate vehicle speed, connected device data, camera health, weather constraints, and active cybersecurity integrity all at once. Mapping these data streams triggers an exponential storage explosion. Primitive 2 applies Tensor Train compression, collapsing this massive grid into a linear chain of bounded cores. Crucially, relationships between variables remain mathematically intact. By utilizing this compression, the system maintains a holistic state tensor of the entire network, replacing an impossible data table with a computable mathematical object. Once the traffic state is compressed, the TNQG framework translates this abstract information structure into operational geometry. It uses a capacity-distance dictionary to redefine physical road networks. In this geometry, a reliable, high-capacity, and highly trusted traffic corridor is mathematically defined as short. Conversely, when that same corridor becomes congested, encounters hazardous weather, or loses sensor trust, its mathematical distance becomes long. This enables topology-native cybercoupling. Cybersecurity is a physical coordinate within the tensor. If a roadside unit broadcasts spoofed data, the affected road segment instantly elongates, actively pushing automated traffic away. Cyber anomalies act as physical geometry constraints that natively reroute network flow, rather than waiting for an operator to notice an alert. Primitive 3 directly addresses tail risk control mechanisms. Optimizing public algorithms solely to minimize average travel time ignores rare but consequential failures. Consider 2 signal timing plans that offer the exact same expected delay. If one carries a small percentage risk of triggering catastrophic intersection spillback, a mean-only objective function cannot tell the difference between them. This chart illustrates delay distribution. The extreme right tail represents rare but catastrophic events like gridlock and evacuation failures. PTCP uses conditional value at risk to mathematically penalize and suppress extreme tail outcomes, while mean-only optimization ignores them entirely. When heavy congestion threatens emergency vehicle preemption or blocks hospital access routes, suppressing extreme delay variations becomes a matter of public safety. Responsible automation must identify and isolate these rare failure states, controlling the risk long before the breakdown actually occurs. Primitive 4 implements a strict, safe actuation layer. Even a highly accurate predictive model cannot be granted unconstrained authority over physical infrastructure. An aggressive AI optimizer tasked with reducing delay might calculate that skipping a pedestrian clearance phase or constantly churning signal timing is highly efficient, even though those actions are illegal and physically unsafe. To prevent this, every machine-proposed action must pass through a strict mathematical boundary called a safe set projection. This filter enforces mandatory operational parameters, guaranteeing compliance with baseline signal safety standards, ADA pedestrian crossing requirements, and municipal transit rules. By projecting every output through this safe set, the architecture mathematically guarantees policy invariance, rendering rogue machine behavior impossible by construction. All these separate components integrate into the complete PTCP and TNQG control loop. Moving left to right, multimodal telemetry is compressed into the Tensor Train, mapped into forecast operational geometry, optimized for conditional value at risk, and projected through the strict safe actuation filter. Primitive 5 provides a final safeguard: TNQG residual testing. The system must prove its internal geometry matches reality. If the model predicts a short corridor, but cameras observe deep cues, an error generates, instantly stripping the model's autonomous authority. True autonomous operation requires a control architecture explicitly designed to catch its own miscalculations and immediately defer to human operators. The formal non-equivalence proof identifies a structural gap in current systems. Any architecture missing these 5 primitives cannot provide the same level of predictive, secure governance. However, migrating to this tensor geometric framework is not a blind hardware swap. It requires a layered, rigorous validation protocol for live infrastructure. The implementation follows strict phases. It begins with passive geometric reconstruction using live data, advances to an operator-facing advisory mode, moves to bounded shadow actuation, and only then authorizes limited, highly constrained automated control. Progress through these stages demands measurable evidence. The system must deliver lower peak travel delays, reduced crash propagation, demonstrably protected vulnerable road users, and active cyber resilience. By uniting high-dimensional telemetry with rigorous physical constraints, the PTCP and TNQG framework replaces fragmented dashboards with a predictive control plane, equipping transportation departments to safely govern the complex reality of modern